Start. So welcome to everybody after the conference dinner. So let's start. Our first speaker is Ettore. Please, Ettore.
Okay, so let's start. As the first thing, I would like to best wishes to Sergio, of course. And the second thing, I would like to thank the organizers for their invitation. And then as a third thing, I would like to present an overview of results on equilibrium and out equilibrium phenomena at quantum transitions. Questo? Lo centrale. Just a moment. Quello sì. Ecco. Devo tenere premuto? Okay. Quantum transitions are transition in the limit of zero temperature between different states, quantum states of matter. Okay. And of course, we are considering here, when we talk about quantum transition, we are generally considering isolated many-body systems. Therefore, they are driven by a Schrödinger equation. At quantum transition, there are interesting phenomena, scaling phenomena, which the systems of quantum transition develop scaling phenomena about continuous and first-order transitions. This is what we will discuss today. But in addition to that, we will also discuss the effects of an interaction with an environment when the system is critical. So it's a quantum transition. And of course, now the dynamics not driven by a simple Schrödinger equation, but it's an extended Schrödinger equation, if you want. I think that everyone knows here what phase transitions are. They are two broad classes of phase transitions: first order phase transition, in which there is a discontinuity, for example, in energy density or in magnetization, and other continuous transitions, which are characterized by a diverging length scale when approaching the critical point. Famous examples of phase diagrams are the one for the liquids and this one for ferromagnets, in which there are both first order phase transition and also continuous phase transitions. Is there a battery problem here?
Allora, dovevi pigiare un po' più soft e comunque puntalo là, perché non so dove hanno messo il corso.
No, il corso fa tutte e due.
Uno più gentle.
Okay. So an important feature of continuous transition is the universality. I mean, you can have the same critical behavior, asymptotic critical behavior, when you consider systems, for example, ferromagnets, or also consider liquids. This is just a case in which we have two transitions, uniaxial magnets and liquids, which can be described asymptotically by the Ising theory. There are another important feature of phase transitions is the possibility that you observe a formation of a condensate. And this is related essentially to the symmetry breaking pattern associated with the continuous transition. A famous transition is the one related to the Bose-Einstein condensation in bosonic gas, in weakly interacting bosonic gas. Continuous transitions are generally characterized by list, say a set of power laws. Here there are number of power laws. I won't enter into the details of what happens at the continuous transition for the thermodynamic quantities, for the correlation function, and so on. And this is the major characterization of a continuous transition. The main ideas to describe continuous transition are related to the spontaneous breaking of a global symmetry, to the existence of an order parameter, to the scaling hypothesis, to the universality I mentioned before, for which the critical behavior, the asymptotic critical behavior, essentially are determined by a few global properties. All these features are nicely encoded in the renormalization group theory, which describes the system in terms of a flow Hamiltonian space. The critical behavior is essentially related to the fixed points of this flow. If you want to summarize what happens at the continuous transition, the best way using write down an homogeneous scaling law for the singular part of the free energy in terms of an arbitrary parameter B, which is a length scale essentially, and in terms of scaling fields, which are analytic function of the model parameters. In a standard transition, we have two relevant parameters. Relevant parameters means that the corresponding renormalization group dimension is positive, while all other scaling fields are associated with the negative renormalization group dimensions, and therefore can be neglected in the asymptotic limit when approaching the critical point. Neglecting the relevant operation, relevant contributions, and setting B, for example, this way, I mean, B is arbitrary, can be set in some way, and one obtains the standard scaling laws for the singular part of the free energy at the continuous transition. Okay, I talked. Those few slides were dedicated to standard phase transition, classical phase transition. Phase transition that are, driven by thermal fluctuations. Let me consider now what happens at quantum transition. Quantum transition, of course, at zero temperature, essentially. Therefore, they are driven by quantum fluctuations. What happens is that for some value of the Hamiltonian parameter, for example, G here, okay, there is a phenomenon of avoided level closing in which the gap closes. And here, for example, in this case, we have a critical interplay between thermal and quantum fluctuations. Again, we have a distinction. We can distinguish between continuous quantum transition, characterized by diverging light scale, like this, okay, and a power law suppression of the gap. While we have also first order quantum transition, they are observed in nature, where the ground state properties in the infinite volume limit are discontinuous. So this is distinction, okay, the correspondence of the corresponds from classical transition to quantum transition. As a paradigmatic model, one can use the Ising chain, the quantum Ising chain, just to understand what happens. Here, this is the model. This is how they are Pauli matrices, sigma 1, sigma 3, and sigma 1. When H is equal to 0, okay, this is a longitudinal field. This is also called a transfer field G. When H is equal to 0, there is a Z2 symmetry. When G goes to infinity, we have a single ground state. So we can associate this to a disorder phase. When G okay, we have a problem with the point. When G sorry. Okay, understand. Okay, when G goes to 0, there are two ground states and therefore they can be associated with the ordered phase, in which there is a spontaneous breaking of the symmetry. The disordered order phases tend to find G up to some point, GC, okay, where we have a continuous quantum transition, characterized by diverging length scale and a separation of the gap. We have also first order quantum transition, the phase diagram of this model, along the line G smaller than GC and H equals 0. These first order transitions are driven by the longitudinal field that we have a discontinuity in the magnetization. These are general phase diagram for quantum Ising models. On the left, I'm sorry, some reason. No. Okay. On the left, we have the phase diagram on temperature, transfer field phase diagram of the one-dimensional Ising chain. On the right, we have a quantum Ising model in larger dimensions. So this is a typical phase diagram of the quantum transition. In the first case, we don't have any transition at finite temperature, just because in one dimension the Ising model doesn't have any transition. Okay. Okay. Around here, we have a quantum critical behavior. There is an interplay between quantum fluctuations and temperature fluctuations and thermal fluctuations. This interplay is characterized by diverging length scale and separation, Pauli separation of the gap. The temperature is a relevant parameter at the quantum transition. Indeed, if we are at the quantum transition, we have a finite correlation length proportional to T to this power. Okay, Z is another exponent, is a dynamic exponent. A guideline to understand the critical from the scaling phenomenon here is provided by the quantum to classical mapping, which is a mapping between a d-dimensional quantum model and a d+1 dimensional classical model. However, the classical statistical system is generally non-trivial because the farther direction, the farther dimension here is generally anisotropic, especially when the exponent is different from 1. Okay, when Z is different from 1. Then we can write down standard homogeneous scaling laws. No. What do you mean? Yeah, okay, your temperature, yes, okay, yes, because you are considering, it's related to the temperature, yeah, you're right. So this is a scaling free energy at the critical point. And this, again, we have a homogeneous scaling law in terms of arbitrary parameter B. This is the relevant parameter of the transition, I mean, R. And then there is a temperature, and then there is a term related to the size of the system. If you fix B equal to L, this can be done, then we find the equilibrium of financial scaling law, okay? Okay, all this, the equilibrium of financial scaling law can be extended to auto-equilibrium phenomena, okay? And auto-equilibrium, for example, the simplest protocol is just a quench protocol. One starts from the ground state, and then one of the parameters, the relevant parameter W here, which is in this case, for example, could be associated with the longitudinal field, is suddenly changed, okay, to another value, and then the system evolves driven by the shredding equation. Okay, we can write down again an homogeneous scaling law. This is a working hypothesis, if you want, for this scaling behavior at this along this quench protocol. And the difference with equilibrium is essentially related that we should add a time dependence. And the time dependence is naturally added in this form here. It's weighted by the gap, I mean, by the behavior of the gap at the quantum transition. And indeed, we associate the exponent Z to the time dependence. Okay, then we fix B equal to L, this is standard, and we find the out-equilibrium dynamic scaling law. Of course, this scaling law must be considered as the limit. L goes to infinity, keeping fixed the scaling value. This is standard renormalization-group theory. Or for example, some results. One may consider in this kind of quench protocols the so-called low-Schmidt overlap or echo, which quantify the deviation of the actual state, okay, at time t with the original one, with the initial one. Okay, this can be computed by computing the overlap. Okay, this is a scalar product essentially. This is the scaling ansatz for this quantity, this logarithm, okay, which is essentially the same scaling ansatz for the renormalization group invariant quantities. Okay, this is the ansatz. These are the variable, and this is a check done on the Ising systems. You can also see that the convergence is very fast. Okay, relatively small size gives shows already the convergence. Of course, analogous results can be obtained using other observables, more standard observables, like magnetization, correlation function, and whatever. But what's important that this is just a soft quench. I mean, soft quench means that during the protocol, the system is always critical, remains critical. Okay. If we change a lot, the parameter, then we put a lot of energy in the system and we excite also the non-critical modes. In that case, we lose the scaling behavior. Okay. So only in the limit of small changes can be observed the scaling ansatz. We have also out equilibrium, okay, arising from crossing of the quantum transition. For example, we can prepare the state, the many-body state, some point for some value of the parameter, for example, smaller than 0. In this case, consider that WC equal to 0 is the critical point. So we prepare it for negative value. We have prepared it at the ground state, then make it evolve using the Schrödinger equation with a time-dependent Hamiltonian, where the time dependence is related to the dependence of the relevant parameter, which change signs at t equal to 0, and then cross. Therefore, during the evolution, we are crossing the quantum transition point. What happens here? Okay, in the limit of when L goes to infinity, since at the transition point, the length scale is diverging, the system is not able to in classical transition would say thermalizing. Here we say to follow the ground state at the given value of the parameter. I mean, to follow an adiabatic evolution. This is not possible, okay, at the quantum transition. So the system goes out of equilibrium. Again, we may consider this process in the limit of very slow passage, okay, very slow time dependence. Ts goes to infinity. And in this case, we can write down some homogeneous scaling laws, okay, for what happens for the out equilibrium phenomena. The homogeneous scaling laws can be, this is again, it's a natural ansatz in which any parameter has its Rg dimension. The Rg dimension is related to Rg dimension of the quantum transition. Okay, we have a time dependence. Okay, this is an arbitrary parameter. This is a generic observable. No, the quantum transition is the dimension. Here, I'm not using anymore quantum to classical transition because this is dynamic. I mean, essentially, you can use the quantum to classical mapping as a guide for equilibrium phenomena. Okay, we are outside. So this is an ansatz, of course. We can, again, this ansatz implies that B is arbitrary. Therefore, we can set it equal to L and derive some dynamic finite scaling laws. These are the dynamic finite scaling laws in terms of appropriate scaling variables. This quantity here is the one controlling the adiabaticity of the evolution. Of course, these answers should be checked, and they have been checked. It's a natural quantity here to describe how far the departure of the protocol from adiabaticity is the adiabaticity function, which again is a scalar product between the actual state at time t and the ground state at the parameter corresponding to time t. Okay, if this is equal to 1, it means that the evolution is adiabatic. If this is not 1, I mean smaller than 1, it means that the system is going out of equilibrium. And this, you can see here some results for the Ising chain. You see that starting from here, start from 1, and then around the transition point, this theta is proportional to t over ts. So when t equals 0, this is the critical point, there is departure from adiabaticity. Analogous results can be obtained for other observables. Some more problems there are when we consider a round trip around quantum transition, but this is the Ising chain. Exponents are exactly known. They are related to the equilibrium quantum transition. You see again. Okay, now, up to now we have considered closed systems. That's a standard context for quantum transition. Now, the question we would like to answer is, what happens if we have a critical system close to a quantum transition when we have also interaction with an environment? And this, to study this kind of problems, different frameworks have been considered. For example, there are studies for some composite systems. In here we have a quantum many-body system, which may be critical, which is coupled to one spin at the center. It's a central spin model. Here we have a many-body system coupled to a set of spins, isolated spins. And here we have, for example, two systems, okay, which are locally homogeneously coupled. One of them can be considered as the system under observation. Okay, the other one can be identified as the environment. Okay, what happens when S is close to, within the critical regime, when we have a weak coupling with the environment? That's the question. Other frameworks which are being considered in the literature is the one based on the Liebland master equation, in which we start, okay, formally from a composite system and derive a master equation for the density matrix of the system under observation. The interaction with the environment is essentially described by this term and by some so-called Lieblandian operators, which can be local or global. There are also other frameworks. For example, one can consider an open system coupled to an infinite number of oscillators. Other framework, it's the Keldysh part integral approach, okay, which are not easy to manipulate. And other frameworks are those studying the effects of projective measurements to the system. Okay, I will discuss a little bit a few of them. For example, let's consider this system here. We have a system. This is the many-body system under observation. We focus on the properties of this system, and we want to understand the effects of this coupling. This is a local coupling. We may consider, for example, to stack the Ising chains, coupled by the longitudinal field. Okay. So, in order to understand the effects, that's the most important quantity is something related to something which quantify the decoherence of the system. To quantify the decoherence, one may consider the decoherence function, which is given by 1 minus the trace of the square density matrix. Okay, if this is 0, it means that the evolution is coherent, and everything is coherent. So essentially, the system is closed, effectively closed. If this is different from 0, okay, it means that the evolution, I mean, so the density matrix is not more related to a pure state. In order to understand the effect of K, when K is small, one may consider this the corresponding susceptibility, okay, which is derivative. Okay, if you expand the coherence function, okay, you can easily see that this is 0. The first term is order K squared. Okay, so you can compute the susceptibility. Larger is the susceptibility, larger is the sensitivity to the external, okay. And when they S, okay, this strongly depends, the behavior of the susceptibility strongly depends on the quantum state of the environment. If the environment is disordered, means which is essentially normal state, we have a divergent with this power L. In any case, there is a divergence. This is standard. Okay, but the divergence can be very different, because in this case we have if YR, for example, is in chain is 1. In the case the state epsilon, the environment is critical, we have another exponent which is 7/2, and the case it's ordered, we have another state which is 15/4. Which so the effects of the environment to the critical behavior of the system under observation can change significantly depending on the quantum phase of the environment. Okay. It's generally. Okay, as I give you an example, but this is, for example, for any quantum instant model of, okay, for this kind of coupling, the exponents are for this kind of coupling. Okay, the exponents are related to the RG dimension on some perturbation at the quantum transition. Okay, one may consider also study the same problem within the other framework, the one considered the Lindbladian equation. Okay, and again, what happens is that this Lindbladian equation, this dissipative mechanism described by the Lindbladian equation, is always relevant. Okay, the exponent associated with this perturbation is always positive. So like the temperature essentially. These are the results. I don't have time to go to the details, because I would like to pass to first order quantum transition. First order quantum transition I usually consider as a very simple. That's not true. Okay, because they show a more various behavior with respect to continuous transition. We will see. As a paradigmatic model, we can still consider the Ising chain. I mean, there is a transition line when G is smaller than GC, and the first order transition is determined by H, the longitudinal field. So we have a discontinuity in the magnetization. But the point is that, okay, again, we can find, as we will see, I write down some final scaling for this quantum transition, actually equilibrium and out equilibrium final scaling, dynamic final scaling for at first order quantum transition. But there is an important difference. The important difference is essentially written here with respect to a continuous quantum transition. At first order quantum transition, the behavior, the scaling behavior of the system is sensitive to the boundary conditions. I mean, when I say sensitive, it means that we can have power laws, we can have exponential laws, so very different. Okay, very different, big difference between different boundary conditions. And these are essentially related to the behavior of the gap of the theory. While at the continuous transition, the gap is always suppressed by power law. You change the boundary condition, it means that you change the amplitude. I mean, here you change the scale, the behavior, the dependence. For example, when the boundary conditions are neutral, okay, for example, periodic boundary conditions, then, okay, the gap is usually suppressed exponentially. Okay, like this law for the dimension. Instead, when we have anti-periodic boundary condition or fixed opposite boundary condition, which induce a domain wall in the system, the low energy physics of the quantum transition is dominated by the dynamics of the domain wall, which is like a particle, for example, in one dimension, and then you find a gap which goes like L to -2. Okay, and this is a big difference. So this difference is also found when we write down the Facets scaling. For example, here it's equilibrium Facets scaling. In order to write down Facets scaling, equilibrium Facets scaling, we should identify the relevant scaling value. And this is quite easy. I mean, the scaling variable associated to the temperature, of course, is related to the gap at the transition point. That's a natural hypothesis. The other scaling variable, which is associated with the driving parameter H, should be the ratio between the energy, okay, induced by the difference of the energy induced by H, okay, which is this. And again, this must be measured in terms of the gap, okay? This is, of course, it's a working hypothesis. It's a conjecture. Then, if we accept these scaling laws and we put 0 temperature, for example, okay, we can write down a scaling ansatz for the magnetization. The magnetization should depend on this phi, okay? Here there are a number of results for the Ising chain which support and confirm this scaling ansatz. But the point here is this is quite general. This is independent of the boundary condition, the scaling law. But the boundary condition are inside the scaling variable, because in one case, when the boundary condition are periodic, okay, the scaling variable is depending exponentially on the size. While the other case is depending, we have a power law. And this is quite general. I mean, not related to the Ising chain. Okay, that's a general phenomenon. Here we have, for example, check for the first case, and we have case for the case in which we have domain walls in the system. Okay.
Demonstrated that because what we have done in introducing the variable T over delta L is essentially engineering scaling. No? So shouldn't you in principle demonstrate that the delta L does not normalize, does not require?
Yeah, but here there is no quantum field theory, statistical field theory. I mean, that I can use. It's a natural ansatz. Okay. So the other interesting point is in this case, okay, we have two states which are very close. All other states are far. And we can compute the scaling ansatz, the scaling functions, by using a two-level model. Okay. Of course, there is a correspondence one must be checked, but it's exact result. This curve here, you see this curve here is a exact computation using two-level models. The Landau-Zinner problem, essentially. All this stuff can be extended. This equilibrium can be straightforwardly, I would say, extended to out-equilibrium phenomena. Okay, and the point is essentially here we had a scaling variable for the associated with the time, and again, okay, we measure when we weight the scaling function using the gap. Of course, this is a general law which holds for different boundary conditions, but this delta could be exponential or could be power law. It's a big difference in dynamics. And so this is likely, and at least that's what I believe, it's likely if you consider Facets scaling frameworks, this is likely the dependence of the boundary condition is likely the major difference between Facets, between first order transition and continuous transition. It's the sensitivity of boundary condition. If you want to understand if the transition is continuous first order, I think the best thing to do if you can check the sensitivity to the boundary condition. What happens when the boundary conditions are changed? This stress that at continuous quantum transition, there is a change, of course, but we are changing only the amplitude. The power law is the same. In this case, we can have exponential and power law, which means a completely different field. Actually, when you have a power law, the results are essentially similar to a continuous transition. Okay. Well, this is a number of concluding remarks. I have time, I can go through. Otherwise, you can read it. Okay. The first point that, I mean, it's the main point is that we can study coherent and dissipative mechanism at quantum transition using scaling frameworks. Okay. I believe that the dynamic scaling frameworks are the best frameworks, okay, to discuss, in particular when you consider finite size systems. Okay. And within this framework, equilibrium finite size scaling emerges in both continuous quantum transition and first order quantum transition. We can have also dynamic finite size scaling. Of course, the context should be correct. We should have that we have a dynamic finite size scaling controlled by the universality class of the quantum transition only when the system is always within the critical regime. Okay, and within the critical regime, we can study the effects of external environment, of dissipative mechanisms like Lindbladian equation, like in the case of Lindbladian equation, whatever you want to study. Of course, this is quite general. All these scaling ansatz, the scaling laws, the ideas are general. They apply to any model, to any quantum transition, and to any dimension. Okay. Checks have been done in one dimension just because in one dimension we know how to do very good calculations. The other important point is that from the point of experiments, okay, the fact that you can observe this system for a relatively small number of variables, you see the numbers, the numerical results that I showed you were obtained up to L equal 20, so 20 speeds, okay? No more than 20, so and we saw, that's not guaranteed, but we saw scaling. Well, this means that all these things can be observed in quantum simulators where there is a problem in controlling a large number of degrees of freedom, controlling that the evolution is coherent in the case of a large number of groups. Okay, I think that's all.
Thank you very much. Questions?
So a large number of properties should depend on the relevant terms in when you go to the dynamical or thermal state. So can your renormalization group distinguish between, for instance, solvable and non-solvable models? Because integrable or non-integrable. Because
it's a very general. You can apply them to integrable.
You know, I mean, the difference appears in the relevant terms. So if you don't keep them, you could miss this difference between integrable and non-integrable. Right. So the difference between integrable and non-integrable typically is irrelevant in the renormalization group sense.
Yeah, I think so. I think that's the problem could be when and that's the difference. I believe that the difference when you consider the large time limit of quench protocols first. But
so you see,
we are always in the scaling region. You see, theta is always finite. Okay, the dynamic scaling law is taken by taking this theta here. Finite, okay? So theta here, okay, is finite. The point you are saying that I mean, issues related to thermalization, if you want, they are not here, okay? They can be studied likely, but I don't think that they are not the main, they are not easily encoded in this framework.
Other questions? Okay, if not, I think we can thank Ettore again. We can